Kestrel 1-1, Mojave Tower, roger. Line up and wait, runway 30, report when ready.
Okay, Kestrel 1-1 flight, line up and wait.
We chose to highlight our 7th flight test because on this mission we made significant gains in Mach number and generated some really interesting testing content that we're excited to share.
Test control, you are go for lineup and a fuel burn of about 400 pounds here.
Copy, about 400 pounds.
We're talking about 400 pounds referring to the fuel burn that we'll need to perform prior to taking off. We overtank XB-1 to give us a little bit of extra contingency fuel for pre-flight checks and taxiing out. 400 pounds may sound like a lot, but all we need to do is run the center engine up to afterburner for about 2 minutes and it'll go away.
Alright, I'm showing us in band.
Test control concurs, I have you in band, you are go for brake release.
Copy, go for brake release.
Kestrel 1-1 flight, runway 30, wind 0503, clear for takeoff.
Kestrel 1-1 flight, clear for takeoff, 30.
Geppetto gave the hand signal that he is about ready to go, and Chase will follow after an 8-second delay. If all goes well, they will rendezvous in the initial right-hand turn right after takeoff. We chose not to execute an airborne pickup on this flight. You can check out the video from Flight 4 if you want to see what one of those look like. But we did this mainly to conserve fuel on the Chase aircraft. Our missions are getting longer and longer, and we don't want to become limited by Chase's fuel state.
3 up and locked.
Clean. Out of burner coming right. A little choppy in the band by the mountains, but nice and smooth now.
Kestrel 1-1, overflight of R2505 is approved at or above 10,000.
Overflight at or above 10,000, Kestrel 1-1 flight.
Nice.
Geppetto is pretty stoked here that we got the airspace clearance we wanted, flying over China Lake Naval Air Station. It's a bit northeast of Edwards Air Force Base, and having access to this area will give us a little more room and should help with test point efficiency a bit.
Test control, your go to load says profile 1 and set altimeter to 90902.
We're queuing up the Flutter Exciter for our first mission test point while we climb to 20,000 feet.
902 set.
Geppetto also sets his altimeter to a setting of 29002, which any pilot can tell you is basically the standard thing to do above 18,000 feet.
Test control, I have card 1 complete. Next up is card 2, 0.7 flutter block.
Copy, card 2.
We've been to 0.65 Mach previously, so the first test point is an acceleration out to 0.7 Mach.
Test is 4-6, good pressure.
Chase is 30.
Alright, I am on condition, ready for Excel.
Test control, your go for Excel to 0.7.
Copy, Excel to 0.7.
Geppetto does what we call a quick look right here and lightly samples how the airplane feels at this new top speed.
Alright, response seems predictable.
From there, it's right into a flutter profile.
Test control, your go profile 1.
Copy, profile 1's loaded. Arm button blue, here comes profile 1.
During flutter testing, we introduce an oscillatory force at the wingtips. This is what the Flutter Excitation System, that we call the FES, does. This essentially vibrates the entire airplane and allows us to measure the damping ratio for each vibratory mode that the airplane has. If you have ever plucked an open guitar string and then lightly tapped over the 12th fret to hear the tone change, you have done flutter testing. Well, kind of. What you sampled were the primary and second harmonic mode of the string. Measuring the time it takes to ring out and become quiet is analogous to measuring the damping ratio. Each part of an airplane has fundamental modes and harmonics as well. It's just a bit more complicated than the guitar string, and the modes tend to interact with one another too. There can be dozens of these modes in an aircraft structure, and we refer to them with terms like wing first bending, second bending, vertical tail torsion, etc. On the ground, they'll all ring out and get quiet pretty quickly, but now imagine playing your guitar in a wind tunnel. At a certain airspeed, the airflow may resonate with the strings and cause them to continually vibrate. Might make for a pretty great music video, but this is really bad for aircraft structure. So we measure the damping ratios of all the vibratory modes on the airplane, both at each new airspeed and Mach number. Airspeed because the force pushing against the surface changes with airspeed, and Mach number because as the airplane approaches the speed of sound, the local shock waves make the center of aerodynamic pressure change locations. These factors can all change the damping ratios, and we must ensure that they stay well damped throughout the entire envelope.
Profile's complete.
Test control, I have profile complete. You're go to load profile 2.
Alright, profile 2 selected. Make just a little check turn for TM. And I am on condition, test is ready.
Control, you are go profile 2.
Copy profile 2, here it comes.
That first profile was an anti-symmetric vibration where one wingtip goes up at the same moment the other wingtip goes down, and the second profile is symmetric where both wingtips go up and down together. It's a balancing act between spending enough time at each frequency to get enough data and not spending forever doing flutter testing and nothing else. After a few flights of trial and error, we have dialed in a technique where we sweep linearly from 4 Hz through 70 Hz over the course of 2 minutes for these profiles, and that has worked out so far. Every airplane will be a little bit different here, and you have to just figure out what works for that airplane and that condition in flight test.
Profile's complete.
Test control, we had a dropout right at the end, but we got past the critical frequency. I have card 2 complete. Next up, card 3, pacer check and SUHQ block.
Copy, out of turn, chaser cleared pacer. Make this turn about 190 or so.
Next up, we're getting into a flying and handling qualities test block. When we say flying qualities, we are talking about the stability of the airplane. Most simply, if the airplane is trimmed flying straight and level, but then experiences a disturbance, will the airplane tend to return to that trim state, or will it diverge away from the trim state without any pilot intervention? That is why we're individually upsetting the airplane in each axis, pitch, then yaw, then roll. We carefully measure the response to these inputs and then trend that information as a function of speed with the same maneuvers conducted at other conditions.
Control, you are go pitch doublet.
Copy, pitch doublet in 3, 2, 1. Mark. Control's quiet.
Test control, trace is quiet. You are go yaw doublet.
Yaw doublet in 3, 2, 1. Mark. Control's quiet.
Test control, trace is quiet. You are go roll step.
Copy, we'll start to the right and come back to the left. To the left in 3, 2, 1. Mark.
This gives us the information to extrapolate a little bit and estimate what the airplane will fly like at the next highest test speed.
A couple brief roll hesitations like we saw in the sim, but overall, good.
Test control, you are go for HQ block.
I'm happy with HQs. We can continue.
Copy. Test control, you're go to begin climb to 23,000 feet at 0.7.
Copy, climbing to 23.
This is the first time that we have ever been to 23,000 feet, and we're evaluating the environmental control system's ability to keep the cockpit pressurized at this altitude.
Test control, I have card 3 complete. Next up is card 4, ECS pressurization test.
Copy.
The compressor in the center engine is the source of pressurized air for the cockpit. So our first test point, we bring the engine to idle and make sure that pressure still holds at that setting.
Alright, I am on condition for card 4.
Lead over the Palmdale vortex and
Control, you
resume our
are set
navigation.
to center throttle to idle.
Alright, center throttle's coming to idle. Is a bit of a decrease in airflow. Cabin altitude's holding 82.
Control, your go, center throttle exam.
Copy, idle RPM 72%, center throttle's coming up. Good response.
In the next test point, we close the valve which supplies air to the cockpit. We expect some pressure leakage here, as evidenced by the altitude within the cockpit climbing slightly.
Test control, your go, step 5, airflow switch off.
Copy. Alright, airflow coming off in 3, 2, 1, mark. Alright, airflow stop. Cabin altitude's coming up gradually.
Test control, your go, airflow switch on.
Airflow switch coming on. Set. Max cabin altitude I saw was 9,800.
The last test point here is similar. It just uses a different valve that we call the bleed air valve, which isolates the air to the cockpit further upstream, closer to the engine.
Test control, your go, step 8, bleed air button depressed.
Alright, here comes bleed air button. In 3, 2, 1, mark.
If there are no leaks in the system, we would expect a similar result to the previous test point.
Alright, similar response. Cabin altitude's gradually increasing.
Test control, your go, bleed air button undepressed.
Alright, bleed air button undepressed. Set. Airflow resumes. Cabin altitude back to 81. Max I saw was 97. Looks good.
Having successfully performed this cockpit pressurization test, we've unblocked a self-imposed limitation against climbing above 25,000 feet. This is somewhat arbitrary, but 25,000 feet is typically regarded as the boundary for high-altitude operations, and we want to make sure that there are no issues with the cockpit environmental controls before sending our test pilot up there.
Test control, your go to descend to 20,000 feet at 0.7 Mach.
Copy, coming back down to 20.
Test control, I have card 4 complete. Next up is card 5, Excel and quick look.
Copy. I'm going to start a left turn. Another 30 degrees of turn. We'll Excel and then we'll get one more turn before we start the flutter.
Control.
Alright, ready for Excel.
Test control, your go for Excel to 337 keys.
Copy, 337.
337 indicated knots at 20,000 feet results in an even 325 knots equivalent airspeed. It's also right in the middle of Mach 0.7 and 0.75, so it's a convenient condition to pause for a brief handling qualities assessment.
Test control, your go for Excel to 0.75.
Copy, 0.75.
As soon as we get to 0.75 Mach, we get right into flutter testing.
Alright, there's 0.75.
Test control, I have card 5 complete. Next up is card 6, 0.75 flutter block. You are go to load profile 1.
Profile 1 selected. Alright, I'm on condition.
Test control, you are go profile 1.
Copy, profile 1. Running.
The flutter tests take the most amount of time to process the data live in the control room for clearance to the next speed, so we do it first.
Profile is complete.
Test control, your go to load profile 2.
Profile 2 selected.
Running up 1902.
Test control, you are go profile 2.
Alright, here comes profile 2.
And flight 1902, Joshua approach the Edwards altimeter 3001.
Alright, profile is complete.
Test control, good sweep, your go pacer.
Chaser, clear pacer. I felt some lateral oscillations on that up to about 30 hertz or so. You guys happy? Okay with that? Alright, 3, 2, 1, mark 343, 20,010.
350, 20,300.
Copy.
And we do another pacer check here, like we do at each new airspeed, to confirm the air data system is still working well.
Test control, we believe that lateral oscillation was FES induced. Okay to continue. And I have card 6 complete, next up card 7. Your go pitch doublet.
Alright, I'll come out of this turn with a roll step. To the right in 3, 2, 1, mark. Feels about the same as it did at 0.7.
Well, good roll step, your go pitch doublet.
Alright, pitch doublet in 3, 2, 1, mark. Controls quiet.
Test control, trace is quiet, your go yaw doublet.
Alright, yaw doublet in 3, 2, 1, mark. Controls quiet.
Test control, much less damped. Trace is now quiet, your go for HQ block.
Copy. Lateral stick movements are kind of setting off a little bit of an oscillation. I'm okay to continue.
Test control copies, you are go for a decel to 0.65 Mach at 20,000 feet.
Copy, decel to 0.65.
We're now in a hold for about 10 minutes waiting for clearance to be issued from the Flutter engineers in the control room before going any faster. So we use this time to collect some data on FES profiles that are only 1 minute in duration at a speed that we have already cleared on a previous flight. The advantage of these profiles is obviously that they're faster than the 2-minute profiles, but they'll come at a consequence of lower data quality. So we're curious if they may still be good enough to clear Flutter test points, because it will make for more efficiency in future test flights.
Alright, I'm on condition.
Test control, I have card 7 complete. We are on card 8.65 Flutter block. Sweep is confirmed. You are go profile 3.
Copy, profile 3. Here comes the profile. Our profile's complete.
Control your go profile 4.
Copy, go for profile 4. Profile's complete.
Test control, your go to climb to 22,500 feet at no greater than 0.75 Mach.
Copy.
And now we're climbing to 22,500 feet to set up for the next speed expansion. We're going to target Mach 0.8, but because we're higher, we will be at the same equivalent airspeed and therefore dynamic pressure as we were at for Mach 0.75. We do this so that we're isolating the variables of Mach and dynamic pressure so that we're only expanding one of them at a time.
Control, I have card 8 complete. Next up is card 9, the 0.8 Flutter block.
Copy.
Test control, we have Flutter clearance and your go for an Excel to 0.8 Mach.
Copy. Alright, rolling out, starting the Excel. Alright, pitch feels good. Roll is a bit, getting some response in roll. But I'm on condition, ready for profile 1.
Test control, your go profile 1.
Copy, here comes profile 1. Alright, profile's complete.
Test control, your go to load profile 2.
Copy. What I'd like to do is the flying qualities block here, and then that way we'll run the profile 2 pointed back toward Mojave.
That sounds good. Test control, I've got you on card 10, and you are go for a pitch doublet.
Copy. I'm going to start a little turn here to flow about 350.
The pilot and the TC are negotiating a little bit here for test point priority, given the constraints of airspace management. It's less important to do the Flutter first this time because this is the fastest test point we have planned for the flight. And so there will be no need for an in-flight Flutter clearance, and we'll just look at the data on the ground.
Alright, pitch doublet in 3, 2, 1, mark. Control's quiet.
Test control. Trace is quiet. You are go yaw doublet. Reminder to be very careful on this. It's not well damped.
You got it. All right, yaw doublet in 3, 2, 1. Mark. Control's quiet.
Test control. Trace is quiet. You are go roll step.
Copy. We'll start to the right and then come back to the left.
We learned a lot about the stability augmentation system on this flight. Subsequently, we have tweaked the gains to make things a little bit smoother at this Mach number.
Alright, a little ratchety again, pretty similar to what we saw in the sim yesterday.
Test control, your go for HQ block.
Copy, we'll get it in the turn here.
Handling qualities testing gathers data on the human-machine interface. It's different than flying qualities testing. What we're doing here is gathering data on how easy it is and to what level of precision a human pilot can perform a specific task in the airplane. The classic way to do this is for the pilot to issue a Cooper-Harper rating for the given conditions and task, with a 1 being the best possible rating, low effort, very easy, and 10 meaning that it's completely impossible. In the specific case here, because this is the first time this airplane design has ever seen this Mach number, we're evaluating the handling qualities of a very basic task, simply maintaining a constant airspeed through straight and level flight, as well as gentle turns for airspace.
Alright, handling qualities appear adequate. It actually feels a little bit better at 0.8 than it did at 0.75.
Control copies.
Alright, I am on condition profile 2 selected.
Test control, your go profile 2.
Alright, here comes profile 2. Alright, profile's complete.
And for this last test point, we're getting into testing the basic airplane with the stability augmentation systems turned off. And we're doing this to make sure that the unaugmented airplane is still safe to fly in the event that the systems were to fault as we continue to go faster.
Test control, I have card 9 complete. Next up is card 11, damper off HQs.
Copy, I'm ready for a pitch damper off.
Test control, your go pitch damper off.
Alright, pitch damper's coming in 3, 2, 1. Mark.
On XB-1, the augmentation is not required for safe operation. It just makes everything feel a bit better. This is different than, say, a military fighter jet, where it might be impossible to fly if the stability augmentation were to fail. Not relying on digital stability control augmentation for a safe flying airplane was one of the major reasons why XB-1 was such a challenge to design, and why it feels so rewarding to have succeeded in this effort.
Alright, pitch is a bit springy, but it still seems pretty well damped.
Control copies, your go pitch damper on.
Copy 13275, chase. Pitch damper's coming on.
It's time I address the elephant in the room. You may be noticing that there's a frowny face on the instrument panel. That little screen there started to display an incorrect artificial horizon on the last flight, which can be very distracting and unsafe. We don't need that instrument because we already have a primary and a backup on that screen to the left, but we also use that lower center instrument as a backup source of airspeed indication, and it's the only one. We're working with a vendor on a fix here, but until that is ready, we just taped over the artificial horizon part, leaving the airspeed indicator visible. The maintenance team has expressed their emotions about this particular component's durability via a silver Sharpie marker.
Test control, reminder to reset altimeter.
Thank you.
Test control, we're going to look for 167 on approach.
Copy.
167 knots. She is referring to the recommended approach speed for landing, which we update every time based on how heavy we are from our fuel state.
Kestrel, standby gear. 3, 2, 1, arc. Alright, 3 down to lock. Dampers on, flight controls auto, anti-skids auto, 165.
Yes, paddles contact, winds are calm.
Test 1.5.
You're live, you're on Sterling.
Our landing signal officer on this flight is Charles Wigware, call sign Wingnut.
You're on glide path, you're on Sterling. You're on glide path, 50 feet. You're on Sterling. 40 feet. 30 feet. 20. 10. 5.
Another perfect landing by Geppetto. Thanks for watching. We really appreciate the interest and stay tuned. There are only a few more test flights left before we break the sound barrier in the world's first independently developed, human-rated supersonic airplane.